Hi there. My name's Nihal, and today I'll be talking about one algorithm for outbreak detection in networks. Let's imagine you're the manager of the entire water distribution system for Atlanta, and this is your network on the right. Suppose that cholera is suddenly introduced into the water supply, and it is your job to detect and contain the outbreak as soon as possible to ensure that cholera doesn't spread. How would you approach this problem? Well, one way would be to put sensors at certain points in the network to detect cholera. That way, you could pinpoint the extent of the outbreak in the water network. Similarly, imagine another graph as a map of Twitter, where nodes are users and edges are followings. Let's say you're a BTS superfan and want to know of any news coming out about BTS. Who should you follow on Twitter to gain the most exposure? Both of these problems are two versions of the same thing, detecting outbreaks in networks. Outbreak detection is defined as given a dynamic process spreading over a network, select a set of nodes to detect the process efficiently. This topic is really important in a variety of scenarios. The easiest one for us in 2020 to visualize is the COVID-19 pandemic, and contact tracing is essentially just outbreak detection. I'll use this image to explain the problem statement for outbreak detection. A is the given network, while B shows the outbreak starting at I and spreading through the network. In C, putting a sensor at the blue position detects the outbreak faster than the green position, but it just so happens that the blue sensor is also more expensive. Beyond just minimizing the outbreak, another goal of outbreak detection is to maximize the expected reward, which includes cost of sensors. The reward can be one of the following three: minimize the time to detection, maximize the number of detected propagations, or minimize the number of infected. The cost depends on the context. For the water problem, it would be cost of sensors. Putting it in a remote location would be more expensive. For the Twitter problem, maybe certain users write a lot of non-BTS posts, so it would take a while to get to the BTS news you need. Next, I'll formalize the outbreak detection process, then explain one of the algorithms used to efficiently generate the max reward. The penalty pi of t for detecting outbreak I at time t can be the time to detection likelihood, or population affected. The reward function f of s for sensor placement s is defined in terms of penalty reduction, and these are the three different cases: time to detection, detection likelihood, and population affected. So before we move on to the algorithm, two claims need to be made. The first is this, on the left. A monotone function means that enlarging the argument set does not cause the function to decrease. If we look back to the three cases for penalty, in all three of them, detecting earlier does not hurt the value, which means that pi of t is monotonically decreasing. Because pi is monotonically decreasing, this can be extended to mean f of s is non-decreasing. I won't go into any formal proofs, but if you're interested, I'll have a link at the end of the video and in the description, which fully explains the proofs. The second claim is this on the right. Submodular functions are characterized by having the property that the difference in the incremental value when adding an element to the set decreases as the size of the input set increases. Below are three cases when sensor X detects outbreak I. The sensor would be an influential Twitter user in the other example. So they are that the sensor detects late, the sensor detects after B but before A, or that the sensor detects early. The point of making these claims is to be able to use an algorithm called the hill climbing algorithm, which optimizes non-increasing submodular functions. To quickly summarize, hill climbing works as an iterative algorithm which first finds a random solution, then attempts to find a better one by making an incremental change. There's two ways to use hill climbing with this problem. Both are bad for our situations. Here's the first one, which is hill climbing that ignores the cost. This is bad because if subsequent sensors have a very small cost, the algorithm will prefer the initial sensor over the cheaper ones. Below that is the second method, which uses a benefit-cost ratio for optimization. This one is also bad because the algorithm will pick a solution but then be unable to afford subsequent ones. One solution to this is to use cost-effective lazy forward selection, or CELf. CELf is a greedy algorithm that combines the two hill climbing methods, then selects the greater of the two. It uses a lazy evaluation of f of s to speed up the hill climbing process. I'll briefly go over the intuition behind this. In the first iteration, marked as A, we use the two hill climbing algorithms and calculate the marginal gains and best sensor placements, denoted by sigma. Starting at the second iteration, you keep an ordered list of marginal benefits from the previous iteration. Then you evaluate and pick the node with the largest sigma, and in B, we reorder sigma for each sensor in decreasing order. Next, we reevaluate each sigma and pick the best one using the previous sigma as upper bounds. Then we repeat the same steps until we get to a maximum. This has the same worst time complexity to hill climbing, but on average performs faster. Running this algorithm, we can evaluate in the water network which sensor placements will capture the cholera outbreak the quickest. In the Twitter example, we learn who we should follow to get BTS information as quickly as possible. CELf's main draw is that it is a greedy algorithm that maximizes submodular functions. Its application can be extended to a wide variety of outbreak detection networks as an alternative to traditional hill climbing methods. I think it's really interesting because a lot of really complex problems like tracking COVID-19 spread can be simplified into a graph and an outbreak. This algorithm greedily chooses the better of two hill climbing methods and maximizes the reward and cost for detecting the outbreak at certain locations. If you want to read more, here are some useful resources that I used. Thanks for watching.